Okay, so to clean up a little bit of the stuff that we skipped over or didn't quite get to in the last class, I want to talk about how we can relate intermolecular pair potentials to macroscopic properties. And this is one of my favorite topics. So the Joule-Thomson effect or the Joule-Thomson coefficient is we typically denote it by mu, and it is how a fluid's temperature changes when you change its pressure while holding the enthalpy constant. Now, which process in everyone's kitchen relies on this coefficient? Refrigerator. This is the key step in the refrigeration cycle, right? We need to take a hot and high pressure gas, or high pressure liquid, rather, and we need to convert that into a lower pressure saturated liquid so that as it goes through the boiler or the evaporator, it sucks all the heat out of the refrigerator and kicks it back out to the condenser, and that's how the refrigeration cycle works. So the Joule-Thomson coefficient from classical thermo is given by this mathematical expression. Does anyone remember what the Joule-Thomson coefficient is for an ideal gas? It is 0. So mu ideal gas is equal to 0. So an ideal gas, the enthalpy is only a function of temperature. So from what we've been talking about with intermolecular potentials, what does the intermolecular potential of an ideal gas look like? So if I were to draw out a plot here of U of R, where R is the separation distance between two gas particles, what should my intermolecular potential look like if I have an ideal gas? 0. Why is it not? So this is what it is. It is just flat. There is no potential energy. Now we talked about the the hard sphere. Why is an ideal gas not a hard sphere? Right, because in the ideal gas approximation, it is one gas particle isolated from everything else in the world. The probability of two ideal gas molecules overlapping is 0. That is the assumption that we're applying when we say it's an ideal gas. Nothing interacts with anything, right? So when you're measuring the pressure of an ideal gas, the only thing that that gas particle sees is its container that it's in. The density is so low that it never will see another particle. So the Joule-Thomson coefficient for an ideal gas is 0. Its intermolecular potential is 0. So intermolecular forces dictate all of the non-ideality in something, let's say, a Joule-Thomson coefficient. In all systems, how molecules interact dictate everything to deal with their non-ideal properties. So, if I were to draw out a Lennard-Jones fluid, so this is the Lennard-Jones pair potential. I'll write U over epsilon, which is one of the parameters. It looks like this. And here this is R over sigma, which is another parameter in the Lennard-Jones potential. And I'm going to draw two possibilities. One where I have state A going to A prime, right? This is an expansion, right? I'm going from a state where the average separation distance is getting further apart. So I'm expanding this fluid from state A to state A prime. I'm also going to consider another option, going from state B to state B prime. Again, this is an expansion. So let's say I'm trying to predict the properties of a potential refrigerant. I have some sort of an experimental basis to come up with my epsilon and my sigma fitting parameters for my Lennard-Jones intermolecular potential. Okay? If I'm designing a refrigeration cycle, should I go from A to A prime or B to B prime? So I have a compressor in my refrigeration cycle. I have a compressor. I compress the hot gas, I condense it to a liquid, so I have a high pressure liquid that's at elevated temperature, and I'm expanding it to a low pressure liquid. Which of these two scenarios should I be designing my refrigeration cycle based on? Should I be going from A to A prime in my expansion valve and my compressor settings, or should I go from B to B prime in my compressor valve and my refrigeration settings? So we've got one vote for B. What else? What else? So take a moment. Think about this. I really, really want you guys to think about this, because this is one of my favorite conceptual questions to ask. So I want everyone to have a vote. Two votes for B. Any votes for A? One vote for A, 2, 3. We have a couple votes for A. Okay, let's walk ourselves through that really quickly. So in this case, we're talking about a Joule-Thomson expansion. So the delta H of the process is 0. Delta H is defined as delta U plus P delta PV. So in this case, delta U is equal to minus delta PV. So let's take a second and let's try and figure out what do we expect the delta U to be between each of these two processes. So if we're going from A to A prime, delta U is what? So we're going from A down to A prime. Is that a positive or negative delta U? It's a negative delta U. So this is less than 0. Now if we go from B to B prime, our delta U is positive or negative? Positive delta U. Delta U is greater than 0. So we would call this exothermic, endothermic. So which of the two is the correct expansion for a refrigeration cycle? It is endothermic. So this is how we would want to design a refrigeration cycle. Yes?
Is that because in the refrigeration cycle you expand into the evaporator and that's where you remove the energy from? And because that's where you're trying to remove energy, like the expansion is in the evaporator, you want it to be endothermic?
Let's take a brief moment and go through that really quickly. So in the refrigeration cycle, okay, so here we have the evaporator. Here we have the condenser. This is our compressor. And here is our Joule-Thomson valve. We have work coming in to the compressor. This is our cooling, Q dot cooling. And we're rejecting heat, Q dot hot. Okay. We have boiled everything, so here we have all vapor. This is all vapor. This is liquid. And this is either a saturated liquid in an ideal sense, but typically it's more so going to be a liquid and vapor here. So this is going to be on the hot side, and this is going to be the cold side. So the reason why we have to do this in the refrigeration cycle doesn't really have to do too much with thermodynamics. It has to do with just basically heat transfer. Well, I guess technically speaking, all of it is thermodynamics, right? Because temperature, well, it's true, it is thermo. Heat goes from hot to cold. So if I need to get heat to flow into the refrigeration cycle and get it to flow out of the refrigeration cycle on the other side, I need to make sure that my evaporator here is colder than the environment that I'm trying to chill. And I need to make sure that my condenser is hotter than where I'm trying to reject the heat to. So the whole point of the Joule-Thomson valve here is that I need to make sure that when I expand my liquid, that it drops to a temperature colder than the environment in the refrigerator that I'm trying to chill, which is why oftentimes you have to defrost your refrigerator, because then ice will build up on the coils themselves, which means it's going to add resistance. It's not going to work as efficiently. A lot of the energy is going to be wasted trying to diffuse that cold through the ice that's built up around the condensers. A good throwback to the very beginning of the class as well. So let's take another quick moment here and let's think about this chart one more time. So what we're saying with this non-ideal fluid and expanding it is kind of very similar to what we talked about with, negative and positive enthalpy of mixing. What we have to do is we have to rearrange this fluid to a condition where it's changing the energy stored in the intermolecular structure, which is what we'll be talking about very momentarily with the radial distribution functions that you've got in front of you. So if I were to take an exothermic mixing process, like water and sulfuric acid, I would have to be breaking the structure of water and breaking the structure of sulfuric acid and rearranging a new intermolecular configuration. As it turns out, for that mixture, it's exothermic. So you're going to a potential energy of the configuration that is lower than two of the individual fluids. Right? So there's less energy that's taking, like getting these two bonds or two molecules to be near one another. So that energy has to go somewhere, and it goes into strictly heating up the fluid. In the case here, with our two options, A to A prime and B to B prime, when we're going from this higher energy, really compressed state, right? We are storing energy in the electronic Coulombic repulsion of the electron clouds. Because we've squeezed these atoms so close together that their electron clouds are starting to overlap. And it takes energy to squeeze those together. If I expand it and I let it to release, that energy has to go somewhere. So the potential energy goes down, but that means that this distance here, or this gap in energy, has to be made up somehow. That energy has to be stored in a new mode. Right? So what we're doing is we're transferring energy from an intermolecular state and storing it intramolecularly in the velocity or the vibrations of the molecules themselves. Conversely, when we're going from B to B prime. We have to steal energy from the individual particles in order to support the intermolecular structure that is at a higher energy state. And that cools the system down. Because the only way that those molecules can give up their energy is if they're at a lower temperature, they have less rotations, less velocity, less vibrations, and then that energy gets stored in this higher energy intermolecular state. So this one example is one of my favorite examples because it ties absolutely everything in together. It ties in mass and energy balances and how we actually design the refrigeration cycle, what we started the class with. Talks about state changes, talks about intermolecular structure, talks about non-ideality, and we even get to throw in a few fun, where is it here? Get to throw in a few thermodynamic partial derivatives. So it's one of my favorite examples to kind of go over. But the key thing to remember is everything that is non-ideal in this world is due to intermolecular interactions. If there were no intermolecular interactions, everything would be an ideal gas. Right? Liquids, solids, non-ideal fluids, everything in the world comes from intermolecular structure. And that segues us very beautifully onto our next topic. Not quite there. Radial distribution functions. The radial distribution function is the single most straightforward way that we can describe what the structure of a fluid is. The structure of the fluid is because of its non-ideality. So if you know the structure, you can basically predict all of the properties. And the radial distribution function gives us all of that information in a relatively convenient way to look at it. So the radial distribution function, oftentimes I'll write R df, or more commonly, it is written as G of R. Now this would be for a 3D function versus G of R, not Q of R, G of R. And this would be for a 1D version. So a 3D radial distribution function tells you the angular dependent fluid structure. So let's say, for example, I had a molecule like benzene, or rather, let's say it's even a little bit bigger, pyrene. This is what pyrene looks like. It's a polyaromatic hydrocarbon with 4 benzene rings put together. This is a highly asymmetric molecule, right? It's planar. There's no flexibility in it because it's all aromatic bonds throughout the whole thing. We would expect that the fluid structure coming out of the plane of the molecule would be significantly different than the fluid structure in the plane of the molecule. Right? And we may anticipate that the next molecule, right, would kind of stack on top of it a little bit. So in this scenario, it wouldn't make a lot of sense to radially average everything, because it would just kind of smear away all the interesting features. But that may be all that you can measure. Now, in the case of a 1D radial distribution function, you are basically assuming that you have spherically symmetric compounds, or that you are radially averaging it. It'll all make a little bit more sense when we actually look at the radial distribution functions. Okay, so what you have in front of you are 2 radial distribution functions. And I think the best thing to do to start things off is to actually look at real radial distribution functions and learn what information is within them, and then we'll go back and talk about how we can determine them and calculate them or even measure them experimentally. So, the key thing to keep in mind about the radial distribution function, right, is that what it effectively says is the probability of finding another particle at some separation distance. All right, so I have one particle. What is the probability that there is another particle some distance r away from it? We're talking about two limiting cases. As r goes to 0, g of r goes to 0. Because you can't ever have two particles overlapping. So the probability of finding another particle right where this one is, or right where I am, for example, is 0. You can't have one. As the separation distance goes to infinity, the radial distribution function goes to 1. It is because it's normalized based on the bulk density. So basically, as soon as the radial distribution function drops off to 1, it's saying that there is no interesting fluid structure at all associated with this mixture. Right? It's saying that you are no more likely to find a particle at some arbitrary position than just as you would expect based on the fluid density itself. Okay, so let's take a look first at the radial distribution function of liquid argon at 91.8 Kelvin. I believe the boiling point for argon is, I think, 130 Kelvin. So these experiments, these were done by X-ray scattering by a gentleman named Henry Eyring. Does that name ring a bell? We have a building on campus here called the Henry Eyring Building. So this is experiments that were done, well, not strictly at the University of Utah per se. They were probably done at the synchrotron or something. But they were done by faculty members here in the chemistry department. We've got two lines on here. There is the solid lines. This is calculated based on some statistical mechanical lattice theory. Doesn't seem to be too bad. And we have the dashed lines, which are the actual X-ray scattering measurements. Okay, first question. What do we think would be a good value for the radius of a single argon molecule? So we have G of R. This is the probability of finding a particle some separation distance r. As we go really far out here, we don't measure any interesting coherent structures, which means that after about 12 angstroms of separation distance, the fluid just kind of looks like a bulk fluid. There's no unique structure going on. So we have one really strong peak, and then we get weaker and weaker. We typically will call these solvation shells. You guys have heard of a term called coordination numbers? Does that term ring a bell? For example, a coordination number might be how many water molecules are surrounding a chloride ion. Right? What's its coordination number? We can get that information from a radial distribution function. So we have one argon molecule, and then we have its nearest neighbor, which is separated by about 4 angstroms. Then we have their second nearest neighbors, which is separated by about 7. Third nearest neighbor, separated by 10. So you can start to visualize what liquid argon looks like. So if I were an argon atom, I would have a collection of atoms surrounding me. I would have some sort of a dead zone where there's no argon. And I'd have another shell around that, dead zone, and then another shell around that, which would be my third solvation shell. But if I had to consider, what do I think is the size of a single argon atom based on this radial distribution function? Someone throw out a guess. Somewhere around there. Because as you go below about 3.5 angstroms, we're getting to a very low probability of finding another particle. Yeah, maybe on occasion you get a really energetic collision and you get those particles close together, but eventually they'll repel themselves. So the probability of having an argon nearer than about 3.5 angstroms is pretty small. So I would say that for a hard sphere, you could say approximately sigma is equal to 3.5 angstroms. So in the book, the Sandler book, this is example 8.1-1 in the Sandler book. It gives the optimized Lennard-Jones parameters that could be used for a molecular simulation. Right? Lennard-Jones parameters are the most commonly used potential. And for the Lennard-Jones potential, the best fitted values, 3.504 for the sigma, and the epsilon over kb is 117.7. So if we were to take these parameters, plug them into the Lennard-Jones potential equation, the minimum energy, U of r, would be at r equals 3.93, right? So if you remember, the Lennard-Jones potential looks something like this. What I'm saying is that the minimum here is at 3.93. It turns out very nicely that that is pretty close to where we see the maximum concentration of the liquid argon molecules. So as it turns out, these argon compounds, they want to be really close together. Right? But the only thing stopping everything from going into that potential energy well is that eventually some things would have to overlap. So the magnitude in this radial distribution function tells us that near one argon molecule, you have a significantly greater, in fact, almost 3 times greater probability of having an argon molecule about 4 angstroms separated than you do the bulk concentration. So near to every molecule, there's a shell where there's a lot of other argons clustered in there. And this is the average across all argons across the entire sample. Okay, so argon is not particularly interesting, but one of the things that's really important is I never quite understood why, before I started doing this myself, I never quite understood, well, why do these physicists care to do these cryo experiments with liquid helium or liquid nitrogen or liquid oxygen, right? Basically, when you're starting off with a simplified system, and this is not, it's a bit old, but it's not super old. Like, we're talking 1981 here. So these experiments were, I guess, it's getting close to 40 years ago, 35 years ago. These experiments here were used to validate the parameters and the statistical mechanical theories that we're talking about now with real systems. And so the reason why people care a lot about a system like liquid argon is because, well, argon, nice noble gas, monatomic, weakly interacting system, spherically symmetric, and it's a big enough molecule that you can liquefy it without too much effort. That's why it's easier to use liquid argon versus liquid helium, because you can liquefy it at maybe 170 Kelvin versus, I don't know what the boiling point of liquid helium is, but it's probably pretty cold. 10, 20 Kelvin, I would guess. Okay, so it seems kind of silly, but it's really useful to validate these theories. Any questions on this before we move to the more complex one, which is water's radial distribution function? Yes?
So when you guess what the radius of an argon atom was, where exactly were you looking for it? Just like as it goes down to zero?
Exactly, yeah. As the radial distribution function here drops off, eventually it'll hit 0. And once you hit 0, then there's going to be no probability that those two things can overlap. Now, a real fluid is not a hard sphere fluid, so there may be some optimum hard sphere parameter that fits the data the best-ish, but in reality, there's always a certain probability of a really high energy collision where you get those two particles to get their electron clouds to really overlap and then go away. So on average, you might have some of those. So you might have some probability of getting two argon particles really close together. But again, these are all just models that are trying to fit the real data. The real scenario is you should be solving Schrodinger's equation for every point in space and every point in time, trying to figure out what is the probability of these particles being in a particular configuration. So each of these models, we're just trying to best represent what's going on here. But this scattering data is the best information and insight that we can have on what is the true molecular fluid structure. And I believe next Wednesday, we'll have a chance to talk a little bit about scattering theory and how we can actually measure these experiments. Okay, let's move on to water. Okay, water is a bit more interesting. So let's talk a little bit about water. I'm sure you guys are all very familiar with this, but let's just boil it down a little bit and talk about some of the complexities that are introduced when we go to to a more complex system. So radial distribution function of water. Now what we'll be looking at is actual experimental data. Now the experiments here are a little bit tricky. You have to do a little bit of molecular modeling with the experiments, but just keep in mind that what we're going to look at is experimentally validated and consistent. In water, as we know, H2O, right, we have two different atom types, H and O. So if I were to draw two water molecules, there are a number of different ways that I can describe its structure. We have three pair correlation functions, or three radial distribution functions. We have G of OO of R, which tells us what is the likelihood of finding an oxygen a certain separation distance from another oxygen. We have GHH. What is the likelihood of finding two hydrogens separated by a particular distance? And then, of course, we have a GOH, the pair correlation function for OH. We have intra-structure, and we have inter-structure. So if I am thinking about a radial distribution function, right, the information contained within a radial distribution function tells us what is the probability of finding a particular atom of a particular type a certain separation distance away. And this is normalized compared to the bulk density of the fluid. So at really far separation distances, the radial distribution function is normalized to equal 1. It's forced to be that way. Should I expect the intra-peak to be bigger or the inter-peak to be bigger? Intra, because every single oxygen has two hydrogens attached to it. So the probability of finding a hydrogen separated a certain distance from an oxygen is going to be exceptionally high. Likewise, we're going to have a HH peak for the intra-structure. And then from there, we can figure out, okay, what are the peaks that are inside of the molecule, and what are the peaks that are outside of the molecule? So let's go back to our water radial distribution function. So which of these peaks is off the charts? OH. What is the bond length of the OH bond? It's about 1 angstrom. What is our next most prominent peak? It is the HH intramolecular bond. It is this one right there. And from there, this is about, about 1.6 angstroms. So you could deduce kind of some of the bond angles associated with what's going on. Because we know what the separation distance is here. We know what the separation distance is here, and we could probably use some geometric considerations to actually figure out what is the bond angle. So by having access to the radial distribution function, we can actually reconstruct what we think molecules look like. Radial distribution functions are measured using scattering theory, which we'll talk about next week. But one of the key questions that I always like to ask people is, how did we know what molecules looked like? Right? When molecular theory was first being developed, right, Boltzmann is typically credited with being the individual to, quote unquote, sort of discover or start atomic theory, right? Of course, Greek philosophers always assumed that there was some sort of indivisible item called an atom, right? So the name's not new. But the first real concrete evidence came from Boltzmann, right, where he was able to develop StatMech and use statistical mechanics to predict the properties of water with extreme accuracy if you assumed that the particles were very, very small. People accepted his predictions of the properties of water because they were really, really good. But they assumed that the properties of an atom were just mathematical approximations, right? Sure, it's easy and convenient to assume that these atoms exist and that they're very, very small, but they're so small that we'll never, ever see them. So only in the past 15 years have we developed experimental techniques where we can actually visualize organic molecules, like benzene. I think it was a Science or a Nature paper maybe in the early 2000s where they did AFM-STM images, and they could actually see carbon atoms bonded in a 6-member ring. So how do we know what benzene was in the 1920s, in the 1930s? We didn't have electron microscopy. We didn't have STM. We didn't have AFM. We didn't have any of these elaborate techniques. X-ray scattering is how everyone discovered what the structure of atoms were, what the structure of molecules were. So these images that we see right here, these radial distribution functions, these are calculated based on diffraction measurements, right? So the Bragg theory, you guys have heard of that, that all came into development in the early 1900s. And then they applied it to crystallized systems. So just how people use crystallography now to figure out how proteins are structured, that's basically just a more complex version of how early chemists and physicists discovered how water was bonded, or how benzene was structured, or what CO looked like, or CO2 looked like. Right? So scattering theory is the basis for all of this. And so a lot of times you'll hear people talk about scattering sort of somewhat dismissively because it is such an integral part of how we understand our world today. And we'll talk a bit about it on Wednesday. Okay, so moving on. So we've got our 2 intramolecular peaks, which are fairly strong. Now, what is our next biggest peak right here? We have our first intermolecular peak. What do we know? What should we call this peak right here? This is our hydrogen bond. This is our hydrogen bond. So we know that the hydrogen bond is a very, very strong bond because it gets two particles that are not covalently bound together basically as close as any other non-covalent bond that we know about. And we can see that this, in water, the hydrogen bond is at about, 1.8 angstroms. We have additional peak over here associated with intermolecular HH bonding, and then we have a very strong prominent peak associated with O intermolecular bonding. And as we increase our separation distance, we can see we have additional solvation shells that correspond to the larger scale structure of the system. And this is where things start to get a little bit complex. It kind of gets a bit harder to break down what's happening. So let's just do a really, really quick compare and contrast. Which do we think is going to be a more structured fluid? Liquid argon or liquid water?
Liquid water.
Liquid water. And let's confirm whether or not that's true based on our radial distribution functions. Here we have our first solvation shell peak around 2 and some change, 2.6. We look at water, we still have about a similar number of atoms in the first solvation shell, but I would argue that you have significantly more correlation. So if I were to draw a line across here as 1, we've got a lot more stuff going on above the line. But things are also skewed a little bit here too. We're looking at argon at 90 degrees Kelvin versus this one at 300 degrees Kelvin. So this is telling us that at 200 degrees Kelvin colder temperature, liquid argon starts to have the amount of intermolecular structure as what we see with water at room temperature. So the higher the peaks that you visualize in a fluid's radial distribution function, it corresponds to the extent of ordering in the system. So let's say, for example, we're looking at liquids here. What if we were looking at a crystal? What do you guys think that the radial distribution function would look like for a crystal? So let's just draw out what we might expect to see. So we have G of R and R. What should my radial distribution function for a crystal look like? It'll be very, very sharp peaks. So we'll have down here 0. So we'll have some amount. We'll have a peak there, and a peak there, and eventually it'll tend up here, and you'll just get a bunch of stuff, and it'll go off to nothing. So by looking at a radial distribution function, you can learn a lot about what's going on inside of the fluid itself. How tall the peaks are tell us what is the likelihood of finding another atom in that separation distance. How broad that peak is tell us what is the range of positions that is acceptable. In a crystal, things are locked in pretty precisely. But there still are vibrations, right? If there's no vibrations, what they call a perfect crystal, you will have delta functions at the unique separation distances. But for any real crystal at a temperature above absolute 0, you'll have vibrations in those crystal positions, and you'll have a broadening of the radial distribution function, and you'll have a broadening of the diffraction pattern. So one of the single most important concepts is that when you ever pick up a paper that talks about molecular simulations, you will always, almost no exceptions, see a radial distribution function plot. And it is so incredibly important to be able to grab that, look at it, and understand what it's trying to communicate. And if you compare two radial distribution functions, being able to qualitatively assess what is this trying to tell me? Which of these fluids is more ordered? Which peaks are important, which ones are not important? And then mathematically, we can additionally extract a lot of quantitative, macroscopic properties out of knowing the molecular structure, right? The whole point of stat mech is that can we take the properties of atoms and how they behave and predict macroscopic properties? Well, what the radial distribution function accomplishes is all of the complexity of that configuration integral that we talked about last class. All of that is lumped into the radial distribution function so that we can use the radial distribution function in place of the configuration integral to calculate macroscopic properties. And it is one of the most important connectors between the microscopic world and the macroscopic world. Any questions on how to read a radial distribution function? Yes?
What would be the difference? These are linear, right?
These are what?
These are linear distributions.
Radial distribution
One
functions.
dimension.
Yes, these are spherically symmetric, or they're averaged.
What would be the difference to 3D that you mentioned?
Very good question. They get really tricky to visualize. So typically what you would see if you had a radial dependent or 3D radial distribution function, the hard part about that is you're trying to communicate 3D information into 2D space, right? So what you could do is, what you could say is, I have a water molecule that I have flattened out into the plane of this screen, okay? I can calculate a radial distribution function, here's the plane, that is in this direction. Or I could calculate one that was perpendicular to it, and I could define an angle theta, for example. So what I could do then is I could have another table here, and I could say this is theta equals 0 degrees, meaning that this is the radial distribution function in the plane of the molecule. And I could have a second plot here that says theta 90 degrees. And I would still have the H, the O, H, and the O, O. But I would be adding 3 additional lines. So to convey the full 3D information, I would have to basically determine which of these peaks are the ones that I care about for whatever particular study I'm working in. And I could plot out maybe the peak G of R magnitude as a function of the angle, or maybe I could plot out the position of the peak as a function of angle. So then it starts to get to be a little bit creative on how would I convey this information. So what I've seen in the past typically done is you'll have kind of more of a heat map, for example. So there's a collaborator of mine has a published paper looking at the structure of liquid benzene, which came out in 2010. So this is the first study that ever really looked at what does liquid benzene, what is its intermolecular structure, experimentally, right? So it seems like we should all know all this information, but there's a lot we don't know about fluids. So what he did in his paper was kind of a heat map, sort of saying, okay, I want to know if I have 2 benzene molecules that are stacked but offset like this, right? They're kind of like this. Not right on top of each other, but offset a little bit, right? What percentage of the benzene molecules have this shape, and where are they located? And then you can kind of come up with like a heat map. Let me choose a different color, saying that, oh, yep, there's 20% are like that. So you can kind of start to build a 3D map of what are the most probable locations. And so with kind of visualization, that's another way to look at it. Strictly mathematically speaking, it's conveying exactly the same information here, except what they're saying is that I'm only going to display stuff that is above this threshold. And then you can start to make a heat map, and then maybe this is red, and then maybe you have another line here where this is green. right? And then you can build a 3D map and say, oh, well, that's the red part, well, here's the green part. And that captures both the peak intensity and the separation distance and the probabilities and all that. But it's a tricky way to visualize it. But the way to think about it, right, is if I'm a water molecule here, I want to know, okay, what's the chance of seeing a hydrogen there versus a hydrogen there versus an oxygen there? That's all the information contained in a 3D radial distribution function. Okay, so let me just wrap up really quickly. How do we get the radial distribution function? Well, we can approximate it with statistical mechanics using something called the Ornstein-Zernike equation. This is one approximation. Basically, it is a very big, complex equation that we're not going to have the time to go through. What's a little bit more tangible to understand this is the most common approach. Is that you can calculate it if you know the positions of the atoms that you estimated from a molecular simulation. And we'll talk about this next week. It could be either a molecular dynamics simulation or a Monte Carlo simulation. Those are two different contrasting approaches that were brought up in that seminar last week, maybe, or 2 weeks ago. And the third approach is from X-ray or neutron scattering. You can experimentally measure the positions. Okay. Any questions before we wrap up? All right. Have a good weekend.